this computer. So Symphony's here. Awesome. All right, so I'm recording this meeting on the computer. So what we're doing is we're starting off with a little warm-up to review estimating reaction enthalpies from bond enthalpies. So in order to get our overall delta H, we have to subtract the sum of the enthalpies of the bonds that form from the sum of the enthalpies of the bonds that break. And so we have 2 carbon-chlorine bonds breaking, and we have 2 hydrogen-fluorine bonds breaking. And from that, we're going to subtract the sum of 2 carbon-fluorine bonds and 2 hydrogen-chlorine bonds, okay? And so when we do that, we wind up with, okay, yeah, that's fine, Sinead, thank you. We wind up with, we got, what do we get, guys? We get, you said we got 18?
Minus 18.
Yeah, that's fine.
Minus 18 kilojoules per mole. Okay, that's great. So you get, so that equals negative 18 kilojoules, okay? And I'm not going to show steps for this because we can all do the math, but it's the sum of this minus the sum of all of this, okay? And that gives us this value right here. And that means that heat is given off or heat is absorbed by the reaction. Which one?
Heat is given off.
Heat's given off.
There you
Very
go.
good. Okay, this reaction's giving off heat. Okay, so I'm going to go ahead and erase this board in 3 seconds. So take a screenshot if you need it somehow, but 3, 2, 1. Okay, so great. All right, so that was the last of it from yesterday. And that's really the end of our series of classes that go through chapter 7. So that was like a remarkably long chapter, but I think part of that is that we have the shorter class periods in the new format, so we're getting used to it. Okay, so now we're going to start reviewing chapter 7. And I want to do a little bit of this today, and then we'll get into on Monday of next week when we have our spring break sessions. So Symphony, are you still there?
Yeah.
Okay, so Symphony, what we were saying is we thought we would all meet from 9:30 to 11 on Monday through Thursday of both weeks of spring break. That way, we're not interrupting anybody's early morning. Nobody has to get up extra early. We're not interrupting lunch. We're just having this nice little, like, you know, meet early enough on, and then go about the rest of our day kind of session on the same days when we would otherwise meet. Does that sound good for you?
Yeah.
Perfect. Okay. All right. So here's our first question, right? And this kind of harkens back to our early notes. So identify the following systems as open, closed, or isolated. Okay. And so I want you to take a look at your own. You might not have your old notes, so let's review it now because some of us probably have our notebooks left at the school. So what's an open system? An open system does what?
An open system can exchange both matter and energy with its surroundings.
Okay. So let's go like system type, and then exchanges matter. Matter, and then heat. Okay, exchanges matter, heat. My handwriting is not that good. Okay, matter and exchanges heat. Okay, so type of system. So an open system exchanges matter and it exchanges heat with the surroundings. A closed system exchanges what? Ethel, do you remember?
I do not.
You do not. Okay. So Mercedes. Okay, Mercedes is trying to log in too. Okay. So Shifa, Mercedes, and April having a Wi-Fi issue. Okay. So a closed system, who remembers what a closed system? Can a closed system exchange matter?
No.
No. But can a closed system exchange heat?
Yeah.
Yes.
Good. Okay. Now we have an isolated system. Right? Can an isolated system exchange matter?
No.
No. Can an isolated system exchange heat?
Nope.
No. Okay. So what are we dealing with here? So coffee in a very high quality thermos bottle. Okay. That one for me is a little bit tough, but take like 20 seconds and think about what you think it should be, open, closed, or isolated, and then we'll talk about it. So what do we think? Is this open, closed, or isolated? And how do we know?
I think it's closed.
Jacob
Closed?
thinks it's closed.
I think
Okay,
I
why?
think it's closed.
Oh, I
Yeah,
forgot my mute was
So
on.
yeah.
in reality, it's going to be closed, but if you use the infinity stones to make a thermos, then it would be isolated.
Yeah, exactly. Uh-huh. That's exactly right. So yeah, realistically speaking, it's closed. Okay. But if you wanted to call it isolated, that
Mhm.
wouldn't be bad. Like for instance, like in
Mhm.
all fairness, like my little water bottle here that I use, it does a really good job of keeping my water cold for 24 hours.
Yeah.
So if you want to say that to a first approximation it's isolated, I'd be okay with that.
Mhm.
Okay. What about coolant in a refrigerator coil? That's hard. I don't even know how refrigerator coils work.
I think that's
I'm gonna
like
call
coolant
that
in a coil used to refrigerate
cool
something.
something. Yeah.
That
So I'm
would
gonna
be
call. So
closed, right?
it would be closed
Closed?
because it's
Mhm.
yeah. The coil is cooling things, right? Okay. Um, and then isolated. What's isolated? Is a bomb calorimeter in which benzene is burned. Is that isolated?
No, it needs to be able to have oxygen to come in.
It's got the oxygen inside.
Oh, that's true.
Yeah, it's a constant bomb calorimeter.
Mhm.
So yeah, that bad boy is isolated.
Okay.
Yeah. Yeah. That's isolated. And then gasoline burning in an automobile engine.
That open?
Yeah.
Open?
Mhm.
Yeah. Yeah. You got the exhaust like that, like the exhaust is being created. That
Right.
stuff's getting flushed out. Yeah, for sure. It's heating the engine for sure. Mercury in a thermometer.
Yeah,
Isolated?
I'd say
no,
it's
that would be
closed.
closed.
Maybe
Yeah,
closed.
because you can heat the thermometer, right? So it
Yeah.
exchanges. It gets hotter, but it doesn't lose matter. And
Yeah, I
then
mean,
a living plant.
Open?
Open?
Yeah, that's for sure open. Okay, that's open. Um, okay, so any questions about this?
no.
All right, pretty definitional. Um, I'll go ahead and clear the share or the screen, and then we're going to move on to 7.3. Okay, so air in a bicycle pump is compressed by pushing the handle. If the inner diameter of the pump is 3 centimeters and the pump is depressed 20 centimeters with a pressure of 2 atmospheres, how much work is done in the compression? Okay, is the work positive or negative with respect to air in the pump? All right, so remember, when we define work, we define it by liter atmospheres,
Mhm.
okay? So liter atmospheres, what's this got to do with that? The diameter of a pump is 3. The diameter is 3. The pump is
Ew.
compressed. So you're talking about the volume of a cylinder?
Yeah.
Okay, so like volume, in this case, I'm gonna help you guys out with this because it's a little brutal.
Mhm.
So you've got volume is pi r squared times
Mhm.
height. So radius is
Right.
1.5. So 2.25
Mhm.
times pi times height. So let's just
Mhm.
multiply 2.25 times 3. That gets us to 6.75. Let's round that on up
Mhm.
to 7. So you got 7 is your volume is your area. Now you're going to multiply that by 20. So 7 times 20 is 140 centimeters
Mhm.
cubed. So you got 140 centimeters cubed, which equals 0.140
Liters.
liters. Okay, that's your volume, right? And so go ahead and find A, the amount of work done, and then B, whether it's done on or is it positive work or negative with respect to the air in the pump? So like, is the pump losing energy or is the pump gaining energy? Okay. All right. So go ahead and knock that out. Take 2 minutes to go through it. It's really quick, but just take 2 minutes to kind of think through it. Hey Siri, set timer for 2 minutes. Okay.
Your timer is set for 2 minutes.
Okay. That's fine. That's totally fine. Yeah, that's what I got too, Caton.
Mhm.
Yep. Yeah, Jacob, I go positive with that because the pump is being compressed, right? The pump isn't expanding against a constant pressure, it's being compressed. So I'd flip that sign, Jacob. Yeah, no worries. Okay. Whew. All right. So that's time. Okay. So I want to hear from somebody who hasn't been sharing through the chat. So I want to hear from Marcella. Marcella, did you get either of these answers?
No.
No. Okay. Um, then let me hear from, well, let me take you through the first one then. Okay. So remember, Marcella, work is in liter atmospheres. So we've got our liters here, right? And how many atmospheres do we have?
2.
2. Yeah. Okay. So it's really pretty simple, right? You just go, to get your work, you go 0.140 liters times 2.00 atmospheres equals 0.280 liter atmospheres, right?
Mhm.
And is the pump expanding against the constant pressure, or is the pump getting compressed?
Compress?
Yes, that's what it says in the question, right? Like somebody's
Yeah.
pressing the handle down, right? It's compressed. So like this is positive work. Okay? The air inside of the pump is gaining energy because it's being compressed, okay? It's gaining potential or elastic potential energy. Okay? So that's what's going on. Does anybody have any questions about this situation? All right, Marcelo, you feeling better about this now?
Mhm.
Good. Okay. Brianna, you all good on this one?
Yes.
Okay. And Sinead, are you good on this one too?
Yes, sir.
Okay. Ryan and Antonio, we good to go, gentlemen?
All right.
Okay. Ryan, you too? I can't see you. Because I've got faces turned off. Okay. So, okay. So I'm going to go ahead and erase the board in 3, 2, 1. All right. And then let's take a look at number 7.5. So 7.5. Okay. A gas in a cylinder is supplied with 524 kilojoules of energy as heat. At the same time, the piston compresses the gas, doing 340 kilojoules of work. What is the change in internal energy of the gas during this process? So remember, delta U equals Q plus W. Okay, where W is the work done on the system. All right, so this shouldn't take too long. Just go ahead and take a minute to refamiliarize yourself. Okay, hey Siri, set timer for 1 minute.
Your timer is set for 1 minute.
See, like Antonio? Yeah, Jacob, I agree. Antonio, I would say no, because remember, the system is being compressed, right? So is the system doing work, or is work being done on the system? There we go, Italy. Yeah, I agree. Uh-huh. Okay, yeah, so Caton
Cool,
says,
cool, cool.
right, okay, good, Antonio? Yeah,
Yeah,
okay.
good.
All right, so, okay, guys, so for this one then, all right, Marcelo, what do you think?
I'm not sure yet. I'm still doing it.
Okay, so,
Yeah, I did the same thing as Antonio, so let me try to.
okay, so yeah, okay, so Nate, let's just go through this together then. So Q is 524, right? So that's being supplied to the system. And then 340 kilojoules are also being supplied. So that's going to give you 864, okay? Kilojoules, that's a positive. So the internal energy is increasing because this guy is being compressed and heated at the same time. So it's gaining a lot of energy. All right. So is it okay if I erase the board?
Yeah.
Sinead, is that okay?
Yeah, you could erase the board.
Okay. In 3, 2, 1, board goes. Okay. All right. So now let's take a look at 7.7 here. Okay. So the internal energy of a system increased by 982 joules when it absorbed 492 joules of heat. A, was work done by or on this system? And B, how much work was done? Okay, so again, same equation, delta U equals Q. That's ugly Q. Q plus W, okay? Where W is the amount of work done on the system, all right? So go ahead and give yourself like let's go with a minute and a half, okay? So hey Siri, set timer for 90 seconds.
Okay, your timer is set for 1 minute and 30 seconds.
Yeah, that's what I got. Yep. But Jacob, I would disagree with the first part of that. Because remember, the system is gaining energy, right? So if the system is doing work, it's giving energy away. If work's being done on the system, it's going to gain energy. There we go. Okay. And then Brianna, may I call on you to answer this for us or to explain your way through this for us?
Okay. I did the last one and I got it, but I keep getting stuck. I don't.
Okay, that's okay. So with this one, the energy of the system, internal energy, increased by this much. So delta U equals 982.
Oh.
And so that equals how much heat was added? Q, how much heat?
It's 492.
Right, plus W, okay? So then that means W must equal 490, okay? And that's a positive number. So that means that work is being done on or done by the system. Which one, Brianna? Do you remember?
Is it by?
No, because if the system's doing work, it's giving energy away,
things,
right?
so
So it'd be a negative sign.
Got it.
Yeah. Mm-hmm.
Okay.
The work's being done on the system, okay? And that's why we do these review exercises. And like, if this is confusing, like, no worries. There's 7.6 and 7.8, et cetera. There are other questions about this in your text, and you're going to see this again too on the AP problems that we'll go over next week. Okay, all those College Board problems. All right, so may I go ahead and erase this board? Any questions?
No.
Okay. 3, 2, 1. Bye-bye, board. Okay, so let's look at 7.9. A gas in a cylinder was placed in a heater and gained 5,500 kilojoules of energy as heat. If the cylinder increased in volume from 345 milliliters to 1,846 milliliters against, yeah, that's fine, Brianna, thank you, against an atmospheric pressure of 750 torr, okay? So 750 torr, that's basically going to be 1 atmosphere. Just round that to 1 atmosphere. It's really 750 over 760 times an atmosphere, but we're not going to worry about that. So just call that an atmosphere during this process. What is the change in energy of the gas in the cylinder? Okay, so go ahead and give this one a shot. All right, and we'll take 2.5 minutes to work on this. So hey Siri, set timer for 2 minutes and 30 seconds.
Your timer is set for 2 minutes and 30 seconds.
Oh, well, we got to know our multiplier. Let me look up that conversion
Yes.
you guys need. Does anybody have
That's
it?
101.325. I just Googled it. The joules to liter per atmosphere
Yeah, what
is
is it?
101.325 joules.
Okay, so 101
Uh-huh.
joules per liter atmosphere. Liter atmosphere, okay. Yeah. And it's joules, not kilojoules per liter atmosphere.
Yeah.
Liter atmosphere, is that correct?
Yeah.
Okay. Yeah, this is funny. Okay. Hey, what's up, April? How are you? April, you said you had some connection issues?
Yeah.
What happened?
Yeah, it wasn't working, but now it is.
Okay. I'm just going to mark you present. I take your word for it. And then April, we all agreed that we would meet. Yeah, that's exactly what I got. But I think this one, Kate, and I think it gained energy, right? It was heated. It gained energy.
Right. No, it gained energy. Oh, yeah,
Yeah.
that's right.
Yeah.
Oh, no. Okay. Yeah, it says plus that and then semicolon, the energy lost from work is mixed
Yeah,
up.
exactly. Yeah, it exerts like 0.1. Yeah, exactly. Okay. So
Mm.
April, we were thinking we'd meet from 9:30 a.m. to 11 a.m. on Monday through Thursday over break. So both weeks, so that we wouldn't meet early in the morning, so nobody would have to get up early, but we also wouldn't run into lunchtime, and that way we'd have our meeting, and then we'd be able to just enjoy or do whatever with the rest of our days. Does that work for you?
Yeah.
Okay. Oh, okay. All right. So let me bust this out. All right. So who can take us through this calculation? Can Idali do this?
Can I do another one? Because I'm not
Okay,
sure.
that's cool. Who wants to do this one?
If I'm being
I
honest, I
can
don't know how to start this one.
You know how to start this one, Sinead?
Yeah, I didn't know.
You don't know how to start this one.
Yeah.
Okay, so shoot me a text next time, okay? Like, or just shoot me a little thing in the chat window, and I'll help you.
Okay.
Okay. So, all right, Rainisha, can you get us started on this one?
I'm thinking. Let's see. I have an idea, but I don't think it's correct.
We'll get us started. What are you thinking?
So I'm thinking that well, just looking at what's given, we know that it's gonna be like a that we have the amount of heat, or we have the amount of heat, and then we have the change in volume
Okay, good.
and
So
the
delta U, right, equals Q plus W, right? Which
yes.
equals, it gives you 5,500 kilojoules
Hmm.
plus W, which you don't know, right? But
Yes.
W is liters times atmospheres times this, right? So how many liters do we have? How many liters are we expanding?
345.
All the way
Or
up to,
no.
right?
Oh, the way up to, so it'd be the difference between those two.
Right. So let's call that 1,500, but that's
Okay.
milliliters, right? So what's the
Yeah.
relationship between milliliters and liters?
Liters, it would be 1.8.
1.5. 1.4. Well, overall it'd be 1.5 because you go from here to here. So you're right. It's 1.8
Okay.
minus 0.3.
Yeah.
Ignore the rest, and then you get 1.5. So this much, right?
Yes.
Times 1.5 liters, right?
Mm-hmm.
Times, right? We've got about 1 atmosphere. Okay? So the
Yes.
atmospheres cancel. Okay. The atmospheres cancel, and the liters cancel, and you get 1.5 times 100, right? Which is going to give you, okay, 150 joules, and that equals 0.15 kilojoules, right? So it's doing work, so that's negative. So we replace this little W over here with, oh, because it's old drawing. I can't even clear the new drawing. Okay, I have to stop this share and start a new share. There we go. Okay. Okay, so that's our new share. So basically what ends up happening is you get delta U equals 5,500 kilojoules minus 0.15 kilojoules, which is roughly equal to 5,500 kilojoules, right? We're just not going to mess with that. So that's all. The internal energy basically doesn't change from the work done. So it's basically all entirely related to the amount of heat added. Okay. So the internal energy is basically or approximately equal to the amount of heat that was added in this case. All right. So I've got a couple chat questions. Let's see what's going on here. Okay. All right. So, okay, good. Yes, good, Ethali, good. And then, yeah, that's fine, April. Take your time. Okay, good. All right. So I'm going to go ahead and, may I erase the board, scholars? Do we have questions?
Go nuts.
Okay. Goodbye, board. Okay, so let's take a look at question exercise. Did I really jump that far? Okay, I don't know why I went with 14 before. That's fine with me, though. Let's go with exercise 7.15. Oh, no, let's go with 7.14 first. Okay, so this is example. This is an example. This one. Oh, yeah. Did we already do this one?
Yeah.
Yeah, but we might as well do it again, just practice.
I think we did this one already. That's okay. I mean, we could do it again, but it's been pretty recent. Let's see if we see it on the College Board problems. So here, let's try this one, okay? So 7.15. So I like this one a lot because this reminds me a lot of an AP practice problem. And we might even just go straight there after a little bit. I don't know if we want to keep doing textbook problems, but maybe it would be okay to do that for now. So each of the pictures below shows a molecular view of a system undergoing a change at constant temperature. In each case, indicate whether heat is absorbed or given off by the system, whether expansion work is done on or by the system, and predict the signs of Q and W for the process. Okay, so, oh, that's interesting. So it's constant temperature, right? But some things are happening. Okay, oh, this is really cool. Okay, all right. So let's take a quick look, right? I want you to be able to see some things. So here, you see these little dashed lines right there? Those indicate that the volume is going down. Okay, so in this first one, right, volume is decreasing. Here in the second one, we start down here, right, and we're condensing, okay? So once again, actually, volume is decreasing, okay? Volume is decreasing in both of these. All right, so go ahead and think through this. Take about two minutes to think through all of this, okay? Hey Siri, set timer for 2 minutes.
Oh, that's weird. I can only think of one substance that does that.
Yeah, me too. Yep. And feel free to shoot me a chat question if you have any questions, okay? Happy to chat with people if this looks confusing or anything. Okay, Italy, your answer doesn't quite fit the format because, like, I would say the first part is correct, but then you've got to talk about Q and W here. What's happening for Q? What's happening for W? Antonio, are you talking about heat? Like, there are 3 different answer parts for each A and B. Okay, so we'll go ahead and talk about this as a group in a little bit, okay? But if you have a question and you're stuck, I will help you. Okay, Marcella, that's fine. Okay, so that's timer. Let's take about another minute to work on this. I think we need about another minute. Okay, so let's start talking our way through this. So let's see. So holy smokes. Okay, so Caton's got a lot to answer. Okay, so let's go through this. So I want to hear first from, let's see who hasn't really like spoken as much with me today. So I want to hear from, yeah, Ryan, let's get you started on this. So Ryan, what do you think's going on in the first one? Is heat absorbed or given off? And is expansion work done on or by the system? And then what are the signs of Q and W? So there's a lot going on there. So what do you think, Ryan, for part A?
For part A, I like to think.
Like first off, what's happening with heat? Is heat being absorbed or given off by the system?
It looks like it's being. Looks like it's absorbing heat
How do you know?
because the solid's turning into a liquid.
Yeah, exactly. Okay. So right there, you know, delta H is positive. Okay. Delta H is positive, right? So heat's being absorbed. Okay. So heat's being absorbed. That means what about the sign of Q? Okay. What about the sign of Q? Q is, right?
I don't know.
Okay. So if heat's being absorbed, is the system gaining energy or losing energy?
Gaining.
Right. So then Q must be positive or negative. Which one? If you're gaining energy.
Positive.
Exactly.
Dr. J?
So Q is positive. Good. Very good. Okay. Kaiten, question?
Oh no, I'm good.
Okay. And then let's talk about the next part of it, right? Because really, these other questions, like, this is redundant. So really, all you need to know is whether Q and W are positive or negative, and then the rest of it makes sense. So it's all related. So the system's gaining heat, so Q must be positive. Okay. And so eitherly is work being done on the system, or is work being done by the system?
On the system?
On the system. Okay. So is W positive or negative?
Positive?
Yeah, W's positive too. Okay, Q's positive and W's positive. And how do you know that work's being done on the system? Either?
Because of the volume, right?
Yeah, when the volume decreases, right, work's being done on the system. Okay,
Okay.
very good. Okay, and then let's talk to Symphony. So Symphony, what's going on in the second example, part B? Is heat being added or is heat being given away by the system?
I think it's being given away
And how do you know that?
because the vapor is turning into a liquid.
Good.
Yeah.
Q's got to be negative, right? Okay. And then I want to hear from Brianna. Brianna, is the system doing work or is work being done on the system? And how do you know?
I said the system's doing work.
Okay, well, remember last time when volume, right?
Okay. So the system's getting worked on. Yeah, that makes sense.
And is W positive or negative?
It's positive.
Good. Okay, all because volume is,
Decreasing.
yeah. So when a system gets compressed, right, work's being done on it. Okay. All right. So, okay. Any questions about this problem? Okay, I'm going to erase the board in 3, 2, 1.
Does that mean when the volume increases, that means it's the work's being done by it?
Yes, exactly. That's exactly what that means. Yes, exactly, Brianna. Great question. That's exactly what happens. Okay, and now we're going to move to a different kind of problem. So we're going to look at, sorry, I just feel like so good to stretch, like any stretching. Oh, feeling great. Okay, so, all right. So like what we're going to do is look at some of these calorimetry questions. Okay, so I love these calorimetry questions because this is like, you know, the stuff that you can learn and know about stuff that you work with. So like, why did my my hot metal spoon burn my mouth when I took it directly from like the oven and grabbed some food with it and put it on my tongue? Well, because it's metal, right? And it's got a very low heat capacity. Okay, so it transferred its heat right away to my tongue. All right, so don't or make sure you notice that there's this little copper specific heat down here of 0.0923 calories per gram unit Kelvin. Okay, and remember the unit Kelvin is the same size as the degree Celsius. So there are a couple things going on here, right? So here's what we're trying to do. We're trying to calculate the heat that must be supplied to a 500 gram copper kettle containing 400 grams of water, and the temperature of the whole system, in the kettle and the water, right, is being raised from 22 degrees Celsius to the boiling point of the water, which is 100 degrees Celsius. So first off, how much heat must be supplied, right? And so let's review our equation. So our equation is Q equals mass times C times delta T, right? And in this case, we have two different masses, a 500 gram kettle and a 400 gram sample of water. Now the copper specific heat, okay, so we got to calculate two of them. We got to calculate Q for copper, and we got the kettle, and we got to calculate Q for the water, right? So that's going to be mass times C of H2O. Okay, and CH2O is 1.0 cal, good Kaiten, okay, per gram degree Celsius, right? Or gram Kelvin, whatever. And this one equals M times C of copper, right? Times its change temperature. And C of copper, okay, is this value right here. Okay, that's our specific heat for copper. So all we're going to do is we're going to calculate these two Qs, and we're going to add them together, right? That's our goal there, okay? So let me go ahead and leave you with that, and let's take 3 minutes to work on this problem, okay? So hey Siri, set timer for 3 minutes. Hey Siri, set timer for 3 minutes. Okay.
Your timer is set for 3 minutes.
And what I don't want you to do is be confused, okay? So if you feel like you're confused, I promise you're just missing something small. So go ahead and shoot me a chat, okay? Shoot me a little message through the chat, and I'll be right here to help. And then, Kaiten, did I get all of it, or did I miss something?
No, think you got all of it. We have the specific heat, so we should be fine.
Okay, perfect. Yeah, delta T is exactly that. Yes, that's correct, Idali. And it's true for both of those equations. Same delta T. Okay, Antonio, that's fine. Brianna, that's not far off. You're just off by a little bit, but yeah, give it another shot. Yeah. Yeah, that's what I got too, Kaiten. Yeah, that's right. Yeah. Yeah. So Kaiten, I agree with you. I mean, of course I approximated everything in my head, but yeah, that's what I got. Yeah, I got
Dr. J, did you see my answer?
I got 32 and 4.
Mm-hmm.
So yeah, hey, Sinead, you crushed it. Nice job.
Yay! Okay.
Yeah, so you got like 32,000 calories for the water, and then about 4,000 calories for the copper pot.
Yes.
Nice job. Good job. Okay. Do you
Do it
guys
up
remember
on the
this from last
board.
week?
Because I don't.
Brianna, you didn't get that? Okay, so Nate, I want you to present this one, okay? So take us through this.
Okay, sorry. Okay, so what's it called? So for copper, I don't know how to explain it. Like it works in my head. I'm sorry.
Plug in your numbers, right? Plug it in. MC delta T. What's your mass of copper?
So MC delta T, the mass of copper is, okay, hold on.
Right here. It's right here. I'm circling it.
Oh, it's 500. Yes.
Good. 500, right?
And then what's
Guys,
And then
I have
you-
to remove the units here. We just don't have room for units on this board. So, okay, 500
Okay.
times what now?
And then you plug in the specific heat of copper.
Yeah, so that's 0.9, 0. That's about 0.1, 0.09.
And then how do I don't know how to explain this. I'm sorry, Dr. J.
What's the change in temperature?
The change in temperature is 78.
Good, right? And that's all
Mhm.
going to give you 4,000.
Yeah.
Okay, roughly, it's actually 3,600, I guess, but 4,000 cal. Okay, little cal. All right, and then over here. Okay, so is Shifa's not here, huh? April, can you take us through this one here?
I don't really get how to do this.
Okay, well, we're going to work on that now then. So what's the mass of water?
400.
400 grams. Okay, 400 grams times the specific heat is 1 cal per gram degree Celsius. Okay, so you've got a gram here. The 2 grams cancel out, and then that's all times. Okay, 78 degrees Celsius. So those degrees Celsius cancel out, and so that all gives you. Okay, and I'm gonna didn't mean to do that. I'm gonna erase this little guy over here. Okay, that all ends up giving you 400 times 78 like that. That's going to give you about 3,200 or 32,000 calories. Okay, 32,000 calories. All right, that's how that turns out. Okay, so does that make sense, April? Is that better now? Okay,
Yeah.
Good. Okay, and so yeah, so that the total number of calories is about 36,000 calories. Okay, or 36 kilocal. And the and that just step away for a second. 36 kilocal, that's like the amount of energy in maybe 3 or 4 potato chips, right?
Well, Dr. J, that does have the big C over there, so isn't that already kilocal?
What has the big C?
The specific heat of copper. Isn't that already measured in kilocal because big C means kilocal?
Oh, did I
No?
look that up?
Oh,
That's me, yo. My fault. Cal like that. I'm sorry, Katie.
okay. So lil cal.
Lil Cal. Yeah.
Also, check it out. I got my C delta T.
Okay. So so next one is but thank you for asking, Kaden. That's really good observation on your part. Keen observation there. Okay. So okay, so we've got, what is this? Okay, so yeah, so you've got about 3,600, 36. So that's the thing, right? So like these 36 kilocal, right? That's you can warm up, you know, you can boil half a liter of water with 4 potato chips, right? Like that's how much heat comes out of those things. That's crazy, right?
Well,
Like
it tells you right now, like,
what now?
well, it tells you right now how much energy our body consumes.
Yeah, it's nuts, right? We put out a lot of heat over the course of a day, don't we?
Yeah.
Okay. So Brianna, did you wind up getting the same answer? Brianna, where'd you go?
I forgot to mute myself.
Okay.
I got that answer. I
You
just
got that
read
answer?
the second one. I didn't. The second part of that I didn't
Okay.
get correct.
Okay, and that's okay. All right. Wow, time flies when you're having fun. Okay, so you got the first answer, and the second part's just roughly 90%, Brianna. So it's like 32,000 divided by 36,000, right? Is approximately 90%.
I probably just plugged it in wrong in the calculator then.
Yeah, that can happen. Okay. All right, so we've got like 4 minutes of class time left. Okay, so no sense in doing another problem. Would you like to see a new pair of shoes?
I do.
Okay, so I'm going to stop